Hey there, let's talk about energy diagrams. We'll use these diagrams to analyze the partitioning between potential and kinetic energy. We can determine the motion of an energy of a particle at a particular position. We can identify turnaround points and stable and unstable equilibrium points. An energy diagram is just a curve of a potential energy function as a function of position, and it's plotted against the energy of the system, or a particle in the system. Because the total energy of a particle is the kinetic plus potential energy, if there's no loss due to friction, we can use a plot like this to analyze the motion of a particle at particular positions. For example, this particle is at the origin, where all of the energy is potential energy. When the particle is at position A, it has some kinetic energy. The total energy minus the potential energy equals the kinetic energy. If it's moving to the right, it must be speeding up because the potential energy is decreasing. When it gets to point B, it's moving as fast as it will be going, right? You can see it has the highest kinetic energy at point B of any position and the lowest potential energy. When it gets to point C, it's slowing down again. And when it gets to point D, it's going slower than it was before. If it goes past point D to point E, it will be speeding up again. Now let's consider a particle that has a lower total energy E2. It could start just to the left of point A, where the potential energy would be the total energy, and then if it moved to the right, it would be speeding up as it goes right. Be going a little bit faster at point A. At point B, it would be going the fastest it could go. At point C, it's slowing down again. When it gets to point D, all of the particle's energy will be potential energy and zero kinetic energy. Here the particle is stopped. This is what we call a turnaround point. The particle is going to turn around and go back toward position C. When it gets to position C, it's speeding up again. When the particle gets to point B, it's going as fast as it can. It has the highest kinetic energy for this energy E2. It'll keep going to the left until it reaches its turnaround point to the left, and then turn back around and go to the right again. This point B is what we call a stable equilibrium. The particle will keep oscillating back and forth about point B, returning again and again to point B. Point D is what we call an unstable equilibrium. If a particle is placed at point D, a small perturbation will push it to the right or to the left, and it won't keep returning back and forth and oscillating about point D. It will go to the right or to the left, but not keep oscillating about point D. This is what we call an unstable equilibrium. Now let's use a PhET simulation of an energy skate park to illustrate how an energy diagram works. Notice I've got the zero height at the very bottom of that dip. We'll pick up the dog to the very top and give him a potential energy that changes to kinetic energy as he goes down, goes back up to the same height because he has the same total energy. Increase kinetic as he gets down, go back to potential as he goes up. Now let's give him some friction. This is going to rob some energy from him, so he can't go back as high again. Goes back lower. In fact, see, he's starting to oscillate. Let's take away his friction. Let him oscillate about this stable equilibrium point. If I pick him up and put him on top of the peak, he can't oscillate about that point in the same way because this is an unstable equilibrium. He can go off and come back, but he can't oscillate back and forth around it. In this configuration, I've given him a higher launch than he has an exit, so he'll be able to jump right off. I give him some higher potential energy, he gets to the bottom with kinetic, and he has enough to go sailing off the end. Now, if I give him some friction, you wouldn't expect him to be able to go as far, because some of that potential energy has been converted to friction energy, thermal energy. I bump up the friction even more. I can show that he's going to go not quite so far. I could use conservation of energy to figure out how far he could go. I could figure out the launch velocity at the end of the ramp. Then use kinematics to figure out how far he would fly through the air. Okay, let's have a little bit of fun with this. What do you think he's going to do when I lift him up and let him go? Give him the highest potential he can have. Should he make it around the loop? Sure, he has enough energy to get up. And he sticks the landing. Very cool. So to recap, we've shown that an energy diagram shows the relationship between potential energy and kinetic energy. Given the total energy of a particle, some E total, the kinetic energy plus the potential energy just equals that total energy. We've shown that the very bottom of the dips are stable equilibria, and the very top of a peak would be an unstable equilibrium if the total energy equals that peak energy. That's it for energy diagrams. Thank you for coming, and come again soon.